Hello everybody. In this section, we're going to talk about applications of double integrals, which is from section 15.3. So we're going to focus on two concepts, area and average. After we're giving those definitions of area and average, everything needed are is going to be calculation of double integrals. That's why this section is called application. So we look at the definition of area. The area of a closed bounded plane region R is given by A equals double integral of R dA. So what it means is, so suppose you have some bounded closed area, we call that as R, and what you do for how big is it, then that's the area. Then to do that, so you need to, the area is going to be, or you can write this A of R, whatever, then this is something like integral of R of 1 dA. What it means is, so double integral is something like you're collecting coins, right? But the coin values are 1 for each spot. So now you're collecting all those things. If you're collecting horizontally, then that gives you one, that gives you 1 dx dy, right, over r. And of course you can change the direction, like you're collecting everything along dy, so dy dx 1, and that is Fubini's theorem. So this is all about this. So the only thing you need to make sure is when you want to compute area of a region, then you put 1 as an integrand. In other words, you're collecting coins with face value 1. Alright, let's look at one example. So find the area of the region R enclosed by the parabola y equals x squared and line y equals x plus 2. So we're going to look at what it looked like. So we have y equals x squared, which is parabola. We don't have to be very precise for the picture, but we need the shape. And y equals x plus 2 is going to be, suppose this is 2, then with the slope 1, the region given by these two curves look like this, the orange area and the yellow area. And to do that, one way is using calculus 1. It is basically, if you think this as f, if we name this as a g, then from calc 1 approach is that just do the subtraction g minus f of x and dx, and you're taking the integral from a to b, where a and b's are a and b's are those left and right end of this region. Now we're going to do calc 4 approach. So our approach by the concept we're given. So we're placing coins with face value 1, then it's gonna be, I will call this as R for the region, and 1 dA. And from the shape, it's not convenient to going horizontal. It's better to collect them in a vertical way. So what I do is 1 and dy first. This is vertical. And then run dx, which means we want to move the stick from very left hand side to the right hand side, all the way from A to B. So the thing is here, given the stick here, what is upper limit? I would say, so y plus, and what is lower limit? Y minus. So I will put y plus here and y minus here. Of course, y plus y minus depends on where the stick is. In other words, where is x is, so in terms of x. And for the range of dx, we need from A to B. So this is the formula we're given in calc form for the area. And let's look at from inner side, what is y plus y minus. So y plus satisfies, so y plus is a point, on f. F is given by x plus 2, right? So y plus satisfies y plus equals x plus 2. Y minus, where is it? So y minus, so the lower end of this stick is lying on the curve of this g, which is parabola y equals x squared here. So y minus satisfies y minus equals x squared. And what is A? What is A and B? What is A? A is intersection of f and g. So B is also intersection of this parabola and line. So we need to find intersections and take bigger number for B, take smaller number for A. So for AB, solve f equals g, right? Which is x plus 2 equals x squared. And from here, we can find x squared minus x minus 2 equals 0. Then this is x minus 2, x plus 1 equals 0. So it gives two solutions. This gives -1. This gives 2. So A is -1, B is 2. Then the next thing is we're going to formulate from here, we continue from here. So the area of R is going to be 1 dy dx, but I need y plus is given by x plus 2, y minus is given by x squared, and dx range is from -1 to 2. And if we compute, now everything is straightforward computation. So we do copy paste, and for the inner one it is y, antiderivative of 1 is y, right? And plug in x plus 2x squared, which gives me x plus 2 minus x squared dx, and then antiderivative, and then plug in those numbers, so we get the area. I'm going to leave the last computation for your exercise. All right, next concept is average value. Right, so average value is given by, so average value of f over r is given by 1 over area of r multiplied by double integral of r of f over the region r. So we often write this as following. So average of f over r is going to be double integral of r of f dA over area of r. So this is the definition of average. So what it means is here now this quantity double integral means if you have some region r and if there's a function f, then f here, the coin face value you placed here, the face value is the same as f, the function value f corresponding to this position for each coin position. So it's not, the face value is not 1 anymore. If you calculate area, then you won't put this equal value 1 for each coin. So for this is total coin value in this region. So that's what you have for numerator. In the denominator, you're going to calculate area. In other words, it is the same thing as you're placing coins everywhere with face value 1. That way we can calculate A of R. All right, next example. Find the average value of f given by this over the rectangle area. So rectangle area is relatively simple. So the rectangle area in the problem is 0 to pi for x, 0 to 1 for y. So for this region, we have function value like this. So average value of f over r is going to be A of r and double integral of r f dA. And here, because of rectangle area, here we don't need to place a coin of face value 1 in the region and take the double integral. This is not necessary because for rectangular domain, we can directly find this as 1 times pi, width times length, which is just pi. So the remaining computation comes from this computing the numerator. So we are going to look at r. F is x cosine xy dA. Well, for this problem, we first look at dy, so which means I'm going to screen the domain in horizontal in vertical way and then shift it. So this is what we're going to compute. So dy range, it is 0 to 1. Dx range, it is 0 to pi. And for dy, x is constant. You can take this out. And cosine x here, xy is sine xy and 1 over x. In other words, the antiderivative of the whole thing is going to be just sine xy. So sine xy and put 0 to 1. Remember, 0 to 1 is replacing y value. So here is y value. X value will remain to the next integration because there is a dx. So 0 pi. And if you put 1 here, the first term sine x, minus, take the difference. When you put 0 into y place, then sine 0 is 0. So we don't have to write anything further. And then this is negative cosine x, 0 to pi. So negative 1, cosine pi is negative 1, minus negative cosine 0, which is 1 plus 1 equals 2. So the answer is, looking back at this problem here, the answer is 2 over pi. Yes, there's no nothing more. So this 2 over pi is the final answer for this problem. All right, we are going to stop here.